Hello friends, welcome to the Applied Polymer Rheology under the edges of Polymer Process Engineering. Dear friends, here we are going to discuss about the structure and properties of deforming polymers. In this particular segment, we are going to discuss about the molecular structure of polymers. Then we will discuss about the stress relaxation behavior, shear thinning behavior, and the normal stresses in shear flow, melt strength and a melt fracture, and dynamic response. Let us talk about the molecular structure of polymers. The macromolecular structure known as polymer, and they are frequently created synthetically but can also occur naturally. Now these macromolecules, they start as a monomer like ethylene, which is represented over here like this. These are the carbon bonds and these are the hydrogen. So this is ethylene. These monomers, they are transformed into lengthy polymer chain with thousands of the repeating units after being polymerized. But they must possess some of the quality through which they can polymerize, like here the double bond or the some sort of the functional groups. This makes them to polymerizable. Now if we talk about the polyethylene molecule, now this represents the polyethylene molecule. Here you see the different carbon things and hydrogen, they are attached together to form the long polymer chain. Now this particular figure, this represents the symbolic representation of the carton of a polymer molecules. So here this is the skeleton molecule and here this can be represented in the form of a chain. So ethylene, this becomes the polyethylene molecule after polymerization. So a polymeric substance is molecularly held together by a number of forces. One force is called the covalent bond, such as CC bond, which keeps the polymer molecules backbone together like this. This is the backbone. And the most fundamental active force, this is the backbone. Now, the relatively low strength of a polymeric component suggests that the force keeping a polymer component together originates from intermolecular interaction, and that is called van der Waals force rather than from CC bonds. According to this particular equation, where epsilon is related to the 1 over r to the power 6, where epsilon is the energy and r is the distance, the energy required to produce the intermolecular attraction between two polymeric material rises as the distance between them decreases. Now this figure, influence of molecular weight on rheological and mechanical properties. Now, the properties of the polymeric material, they are closely related to the number of repeat units n. Like here, you see that these are the number of repeat units. Now, in the molecular chain or the molecular weight of the polymer, this is directly proportional to the number of repeat units or number of chains. So, polystyrene is a polymer with a degree of polymerization of 1000, is stiff and brittle at room temperature. Now, at room temperature, if we talk about the molecular structure of polymer, at room temperature, the polystyrene is soft and sticky with a degree of polymerization of 10, while the viscosity grows continuously with molecular weight. The stiffness qualities attain an asymptotic maxima. During the processing, several thermoplastic, including some polyamides, 1,1 resin, this increases the molecular weight. This causes the viscosity to increase and could lessen sag as the polymer comes out of the extrusion die. So this need to be addressed. So this particular figure reflects the molecular weight versus stiffness and strength and viscosity simultaneously. Now this particular thing is valid for thermostats which cross-link or cure during the processing. Now when the gel point is achieved, During the curing process, the material is regarded as the solid because the molecular weight of the material grows. Now, rheology is the field that studies these impacts. Let's talk about the stress relaxation behavior. The stress relaxation is the most fundamental behavior in polymer melts and solids. Now, as a mass of polymer is subjected to a stress, the molecules tend to move in an effort to relax those stresses. The initial stress brought on by this deformation relaxes in a specific amount of time and frequently referred to as the relaxation time lambda if these stresses are brought on by a constant strain. Now, this particular figure represents the relaxation modulus polyisobutylene at various temperatures and corresponding master curve uh, at 25 degrees Celsius. The stress relaxation modulus of polyisobutylene is determined the various temperature which is shown in this figure. Now, this stress relaxation modulus is determined by this equation. ERT is equal to small sigma T over epsilon naught. This epsilon naught is the applied stress and this function is the stress being measured. In particular, around the glass transition temperature where the slope of the curve reaches its maxima, it is evident that the stress relaxation is a time and a temperature dependent, and the glass transition temperature for the polyisobutylene depicted in this particular figure is around 70 degrees Celsius. So, the experimental time window, this is the measurement ranged from the few seconds to 1 day. Now, the tests conducted at a lower temperature, these were utilized to capture the beginning of this relaxation of the rapidly decaying stresses, while the tests conducted at a higher temperature only recorded the conclusion of the relaxation. Now, this is the schematic stress relaxation on the molecule level at low top and high bottom temperature. It is commonly known as the low temperature provide long relaxation time for molecules and high temperature causes the short relaxation time. As this crudely depicted in the form of entangled or a loose chain. This results from the fact that at a low temperature, the free volume between the molecule is tiny, so that all these chains are entangled all together. And if we raise the which restricts and slow down their movement, but if we raise the temperature, then the free volume between the molecule is become larger and they may become like loose like this. So, the form of the finding from the creep or a relaxation like here you see does not change as the temperature changes, but they are horizontally displaced to the left or right corresponding to the slower or faster response time. Now, here you see the molecular structure with increasing shear. Now, this is the entangled molecules. They have the difficulty in slipping past one another at the modest rate of deformation, leading to a relatively high viscosity. So, they are very much compact in nature. Now, this behavior can be observed at a variety of small deformation rate for the polymer melts. So, here you see they are trying to unentangle and they are adopting the flow behavior. Now, constant high viscosity is referred to as the Newtonian plateau, which is referred as this one. However, as the rate of deformation rises, the shear stress that results rise in the proportion and is high enough to separate and unravel the molecules, which is represented as like this. Now, because of this entangled molecule can pass their neighbors more easily and viscosity of the melt is generally reduced, the shear thinning behavior, the pseudoplasticity or structural viscosity are termed used to describe this particular phenomena. The molecules eventually reach their limit of extension. Here you can see. Now, this particular point, which represents the lowest attainable viscosity, can be seen in the second Newtonian plateau at high deformation, which is represented over here. Now, as the temperature rises, the free volume between the molecule expands, reducing the intermolecular friction and resulting in a reduction in viscosity as per this particular figure. Now, this is the schematic diagram for met at rest and a normal stress reaction during the shear flow. This is the normal stresses in the fluid originate from the tendency of the polymer molecules to curl up while they are stretched in shear flow. Now, as a shear flow that exhibits a deviatoric stress, which is defined by the equation tau xy is equal to neta gamma for the flow behavior T into gamma xy, where the gamma xy is the rate of deformation tensor and T is the temperature. Now, normal stress differences are defined as measurable reactions perceived in the form of a normal stresses originating from the molecular structure. So, N1 is equal to tau xx minus tau yy and N2 is equal to tau yy minus tau zz. Now, this effect is schematically depicted in this figure where the stress differences referred to as the first and second normal stress differences as per this particular figure. Now, this is an experimental setup representing the normal stress differences effect is the so-called rod climbing experiment and also known as Wiesenberg effect. The polymeric solution, this moves towards the rotating shaft in this experiment instead of away from it as with the Newtonian fluid. The polymer consequently begins to ascend the revolving shaft. Now, this is the schematic representation of a normal stresses in the cuvette flow. The normal stresses develop as the shear stress of the cuvette devices stretched the polymeric molecule. The rod climbing phenomena is caused by the stretched molecule's tendency to move in the direction of the spinning shaft because they are aligned along the curvilinear streamline. The normal stresses, just like viscosity, they are also the material dependent and can be defined as N1 is equal to tau xx minus tau yy, that is equal to psi gamma t gamma xy square, and N2 is equal to tau yy minus tau zz is equal to psi 2 gamma t gamma xy to the power 2. The primary and secondary normal stress coefficient denoted as psi 1 and psi 2 respectively are the material function. Now, these properties are dependent on both the magnitude of the strain rate tensor and the temperature. Similar to viscosity, the first and second normal stress differences remain unchanged in sign even when the direction of the strain rate is altered. The second normal stress differences, they are more difficult to measure and therefore the data they are often approximated by psi 2 gamma is almost equal to minus 0.1 psi 1 gamma. Now, let us talk about the melt strength or melt fracture. The melt fracture, they are also known as the plastic deformation, occurs when a polymer is forced to deform and move at rates that cause processing time that are less than the polymer's relaxation time. Now, this particular phenomena might appear in several ways depending on the method. For example, high extrusion speeds that prevents the polymer from relaxing inside the extrusion die may cause waves to emerge in the extrudate. Here you see the different type of other things. The high shear forces between the polymer and the die wall are to blame for this particular phenomena. It is also known as the stick slip effect or spurt flow. It happens when the shear stress is close to the critical level of zero point 0.1 megapascal. Here you see the influence of the molecular weight on the slip between the polymer and tool surface. This is the low molecular weight polymer molecules, and this is the mold surface. You can see the effect. And similarly, you see that these are the contact points. So this is the high molecular weight polymer molecule, and the contact points are more compared to the low molecular weight polymer molecules. However, if we talk about as a roughly depicted as per this particular figure, impacted by the molecular weight of the polymer, a high molecular weight polymer molecule has more contact sites which in the surface. As a result, a polymer with the high molecular weight has superior melt fracture resistance than one with a lower molecular weight, because the number of contact points, they play a very vital role. According to the source, the weight average molecular weight has an inverse relationship with the critical shear stress of 0.1 megapascal. A different type of melt fracture may happen during the elongational deformation, such as during the spinning of fiber. The excessive drying speed causes tensions to build up before they have a chance to dissipate, resulting in a thread tear or fracture. Let's talk about the dynamic response. Oscillatory test, a sample is aroused by a low frequency stress or strain input, and both the stress or strain responses and input are recorded. In this particular figure, you see that the oscillatory shear experiments of for an elastic solid, a viscous fluid, and a viscoelastic fluid. This figure shows the schematic diagram of shear strain input gamma xy and shear stress response tau xy for a perfectly elastic. This particular figure shows the schematic diagram of a shear strain input by gamma xy and a shear stress response tau xy for a perfectly elastic solid, an ideal viscous fluid, and a viscoelastic fluid with a linear viscoelastic response. The strain input and stress response in an oscillatory test, this can be explained if the sample is a Hookean solid or a perfectly elastic, and that is gamma xy t is equal to gamma naught sine omega t, and tau xy is equal to tau naught sine omega t, where t is the time and omega pi t, omega is equal to 2 pi f, with f being the frequency of strain oscillation. The stress response and the strain input in phase, as would be predicted. As a result, when the computing the shear modulus, the transient effects are cancelled out, leaving the resultant elastic modulus g, and which can be represented as g is equal to tau naught sine omega t over gamma naught sine omega t. The stress response, on the other hand, is proportional to the strain rate gamma naught omega cos omega t, which may be alternatively be understood as a lag of pi by 2 radius after the strain input when an ideal viscous fluid is subjected to an oscillatory strain. So, this is gamma xy t gamma naught sine omega t, and gamma xy is equal to gamma naught cos omega t. So, here tau xy t is equal to tau naught cos omega t is equal to tau naught sine omega t minus pi by 2. Now, where omega gamma naught is equal to gamma naught omega, using this particular equation, we can compute the viscosity using the definition of a Newtonian fluid, which says that eta is equal to tau cos omega t over gamma naught cos omega t is equal to tau naught gamma naught dot. So we see here that the transient effects cancel each other out and resulting the constant viscosity. However, the viscoelastic material such as polymers, they behave somewhere in between the perfectly elastic and the perfectly viscous material depending on the time scale. Now, their representation can be described by gamma xyt is equal to gamma naught sine omega t and tau xyt is equal to tau naught sine omega t minus delta. Now, this showing the stress response uh, of lag of delta radius behind the strain input. Now, the shear modulus computed using that particular ratio of stress to strain, this take a complex form with real and imaginary term and can be written as G star is equal to tau x t over gamma x y t. This is equal to tau naught e to the power I delta over gamma naught and tau naught over gamma naught cos delta plus I sine delta, and this is equal to G prime plus IG double prime. Now, this is shown in the figure and referred to as a complex modulus, and the length of each vector represents the absolute value of the parameter. Therefore, G prime is the resulting vectorial sum, and G prime is usually referred as a storage modulus and represented by G prime is equal to tau naught over gamma naught cos delta. Now, it is the measure of during a shearing process can be measured upon release, and this energy can be fully utilized for the recovery of deformation, rendering it reversible. And the loss modulus, this is denoted by G double prime, quantifies this particular phenomenon and can be calculated using the different equations. Now, G double prime is equal to tau naught gamma naught sine delta. Now, the loss factor or the loss tangent is measure of the energy dissipated or utilized for structural changes in a material such as heat generation, and therefore the deformation alters ideal viscous material, rendering the process irreversible. The loss factor is determined by the ratio of the loss modulus to the storage modulus and referred as tan delta is equal to G double prime over G prime. Now, in an elastic solid, delta is equal to 0 and tan delta is equal to 0 and G prime dominates G double prime completely. However, in a viscous fluid, delta is equal to 90 degree and tan delta is equal to infinity or tends to infinity, and this G double prime dominates G prime completely. Now, in viscoelastic material, the tan delta is equal to or greater than 0 and less than equal to infinity, depending on the time scale and temperature. When the viscous and elastic behavior are equal to, delta is equal to 45 degree or tan delta is equal to 1, the material is making a transition from liquid to solid or vice versa. For example, this occurs during curing of a thermoset when the system reaches its gel point, and in the liquid state tan delta is greater than 1 as G double prime or G prime, and after gelation tan delta is less than 1 as G prime is greater than G double prime. Similarly, when the test is regarded from a rheological point of view, a complex viscosity can be computed using the rate of stress to rate of deformation. Now, this can be represented as neta is equal to tau xy over gamma xy t is equal to neta prime plus neta double prime, where this one is the viscous component of the complex viscosity. This is also referred as the dynamic viscosity, and neta double prime is the elastic component, also referred as out of phase component of a complex viscosity. The relaxation between the complex modulus and complex viscosity component, this can be described by neta double prime is equal to g prime over omega, and neta prime is equal to g double prime over omega, where this neta double prime, this represents the elastic and this neta prime represents the viscous behavior. This complex modulus representation is often used in industrial testing. So, dear friends, in this particular segment, we discussed the different type of a rheological behavior with the grassroot polymer chain phenomena. And for your convenience, we have enlisted several references which you can utilize over the period of time if required. Thank you very much.